So, let us continue with some more examples. Second example, for every vector x in a vector space V, the scalar multiples of this vector k times x, this is all those Ax as A varies in the field K. This subset is clearly a subspace of V. This one can see easily by using the subspace criterion we have given, and this, and it is the smallest subspace containing the vector V, vector x. So, it is also called a vector subspace generated by, it is also called the subspace generated by x. Now, some more examples I want to note, for we will use them further in our lectures. So, let D be a subset of this special symbol for k, where whenever I write such a k with a double line, this is either R, the field of real numbers, or the field of complex numbers. You can take either of them, and the statements I will write, they will be valid for either case. So, the set of all continuous functions on D to k is a subspace of the k vector space k power d. Last time I defined what is k power d. They are all functions from d to k, and we have seen that form vector space over k, and among them we are taking the continuous functions. So, this is immediate, because in the first course on analysis we check that sum of two continuous functions is again continuous. Continuous function multiplied by a scalar is also continuous function. So, therefore, by subspace criterion, the space of all continuous functions on D with values in k, it is a subspace. This subspace I am going to denote by C for continuous, k here, that is k valued, and the domain is D or 0 here. So, sometimes I will just write CD, continuous functions on D, or sometimes also I write it C suffix k, just to remember where the values are, values of these functions. So, this is the standard notation, and a first course on analysis is devoted to study of this subspace. Okay. Continuing further, fourth example, let us now take the interval. Let I contained in R be an interval. Which has more than 1 points, with more than 1 point. So I want to avoid the situation like intervals like this A. I want to avoid this. That's why it should contain more than 1 point. This contains just a singleton here. And let n be any natural number. Then the set C n R I. This is the set of all f I to A, I to R real valued functions on I, and f is n times continuously differentiable. That means f prime exists and it is continuous, f double prime exists and it is continuous. This happens till n. F n are all continuous functions. And these are the derivatives. This is the first derivative. This is second. And so on. So this is also a subset of C 0 R I. And it is a subspace. Set is a subspace, is a R subspace of C0 Ri, which is also subspace of R power I. This is the ambient vector space and this is a subspace and this is a further subspace of that. And I could have done the same thing for, instead of real numbers, complex numbers also. So in general we have a big family. In general, okay, just to how does one check this is one needs to note that if you have two differentiable n times continuous differentiable functions on an interval, then their sum is also continuously differentiable. That we have seen again in the first course on analysis, and the derivative is the sum of the derivatives. Similarly for the scalar multiple. So this is obvious from the subspace criterion. So in general we have a big family Cn, K, I, n in n. This form a descending chain of K subspaces. That means the C0 is here, these are continuous functions on I, k valued continuous functions on I. Then comes C 1 once differentiable and once continuously differentiable, then 2 times continuously differentiable, because you know if it is differentiable then it is continuous. So we have a descending chain like this. If you have studied more analysis, then you would note that at every stage this inclusion is proper. That means you have to construct functions which are n times differentiable but not n times continuously differentiable, but not n plus 1 times continuously differentiable. And constructions of such functions is usually done in the analysis course. I just want to say here the first inclusion is easy really, because if you look at this function, the graph of the function whose graph is this you can take on the interval 0 1, you take this 10 function. This function is continuous, but it is not differentiable. At this point it is not differentiable, because differentiability means a tangent should be well defined, and here the tangent is not well defined. So this is the example for this. Now from year to year you will have to work more and more harder to find functions and so on. Okay. Continuing still further we can say something more. If you take their intersection C n k I, so this is the intersection of all these subspaces. This is also subspace, because we have seen just above that intersection of arbitrary family of subspaces is again subspace. This is a k subspace. Again, if you like, we are working in this big ambient space, function space k power I. This by definition it is denoted by C infinity k. This is the set of all infinitely many times differentiable. So this is also subspace, and such subspaces are very important to study in analysis. Even one can also construct examples which are n times differentiable for a given n, but it is not infinitely many times differentiable. Okay. Now one more subspace I want to define, and then we will go on to some other examples. C omega ki. This is the set of all k valued analytic functions on I. Oh, what is analytic function on I? That means a function f. So this is all those f in k power I. F is analytic on I. Analytic on I means it is analytic at every point in t in I. F is analytic at t means in a small interval around t minus epsilon to t plus epsilon. This is a small neighborhood of t. In this interval f should look like a power series function. F has a power series expansion on this small interval t minus epsilon to t plus epsilon, where t is a point there. So that means f of t looks like, or f of x, f of x look like summation n x power n on t minus epsilon t plus epsilon, where this side is a power series, convergent power series. I will not go much into other details. So this is, so what to note is, this is a subspace C omega ki is a k subspace of k power I, and C omega ki is in fact a subspace of C infinity ki. So this means every analytic function is infinitely many times differentiable, and you might have learnt in analysis course that the derivative is given by term differentiation of the power series expansion. Also here this inclusion is proper, that means this is more tougher to construct example of a analytic function, example of a C infinity function which is not analytic. Such functions usually arise in probability. Okay, so enough of these function spaces. This example was completely devoted to the subspaces which arise in analysis. Now let us coming back to the next example. I have forgot the number, so I will check the number. The fifth example. This is sort of example from algebra. So let K be a field, K field. It could be finite field also. In fact, I will show you later sometime that this is more interesting when K is a finite field. And D any subset of K, any subset. Then we have this big ambient space Kd. These are all functions, all K valued functions on K, and we have seen in the last lecture that this is a K vector space. Functions are added like their values are added. Also, a scalar multiplication of a function is defined by using a multiplication in the field K. Now among all the functions, I consider what is called a polynomial function. So polynomial, let us recall what is a polynomial function. On D. That means we have a function of the form, a function from D to K of the form any t going to a naught plus a1t plus a n t power n, where these a0 to an are elements in K. And they are fixed. A0 to an is fixed. These are called coefficients. So such a function is called a polynomial function. Polynomial function. If D is finite, if D is a finite set, finite subset of K, then every function on D is a polynomial function. Why that? Because note here, this is something like interpolation. So since I will write here the reason, since for finitely many distinct points T1 to Tr in K and given values B1 to Br in K, you know there is a polynomial f such that f of Ti is Bi. So this is, if you remember, it is interpolation. There are two ways to construct such polynomials. One is called Lagrange interpolation. And the other is Newton interpolation. I will more about this I will write in either in supplement or in assignment. I just want to recall that both of these also involve derivatives. Okay. Okay. Continuing further, if D is finite, if D is infinite, sorry, if D is finite case is over, if D is infinite subset, then the coefficient of a polynomial function remember I have written a polynomial function as f of t equal to a0 plus a1t plus a_n_t, where these coefficients a0 to an are elements in K, they are fixed and we are calling them coefficients of f, and this is valid for all t in D. such a function we call it a polynomial function. The coefficients are uniquely determined if d is infinite. A0 to an are uniquely determined. This follows from the fact that if you have a polynomial, then it is determined by its n values, because if you have a polynomial which vanishes at more than the degree 0, then the polynomial must be 0. This is a consequence of the fact that every polynomial has at most degree f degree, let me call every polynomial p with coefficients in k, has at most degree p zeros in the field k. This fact maybe I will prove sometime in a later section, but right now we have used it in this example because d is infinite, and such a polynomial, if there are two, if the coefficient, there is other set of coefficients which also satisfy this equation, then the difference is a polynomial function which is identically 0. So, but it has more, d has more than this given n points, so therefore it should be 0. So, it is identically 0, that means all the coefficients are equal. Okay. This about study of the polynomials I will do it in a different section, but this was just to give an example. Okay. So, if I denote the set of all polynomial functions temporarily by kt, where I am again I want to recall this was for so far over a general field, but now I take k equal to either field of real numbers or field of complex numbers, and then this kt, let's denote the set of all polynomial functions. On the interval I contained in R. Then this kt is actually subspace of C omega. Just remember, just now we have seen this C omega ki is the space of all analytic functions on the interval I, and we have seen it is a subspace, and analytic means every point has a small interval around it where this function has a power series expansion, but these are actually polynomial functions. So, in particular they are power series expansion. So, that means polynomial functions are analytic functions. So, this means, this inclusion simply means polynomial functions are analytic functions. And here also there is a proper inclusion, because simply because you would have seen exponential functions are analytic functions, but exponential functions are not polynomial functions. So, that is the reason this inclusion is very proper. Okay. Now, with this I would like to continue the study of subspaces. Okay. So, continuing continue with the study of subspaces. if you have a let always I will once again recall K be a general arbitrary field and V be a K vector space. Let Ui I in I be a family of subspaces of V. Then the smallest subspace containing all these UIs. Such a smallest subspace exists because V is one subspace of V which contain all UIs. So definitely there is one subspace, and when you want to take smallest, you take the intersection of all of them which contain all the UIs. Then this is, we have seen intersection of a subspace is subspace, and this subspace exists, therefore it is the smallest one. This subspace is denoted by, is called, first it is called the sum of UIs and is denoted by, it is called the sum, it is denoted by this UI, I in I. Actually we can write down the elements of this subspace. This is precisely the set of all sums xj's, where j in j is a finite subset of I, and xj they belong to uj, j belongs to j, and j is running over all finite subsets of I. So in other words, you look at the finite sums of the finitely many sums of the finitely many elements from UJs. So how does one check the equality? It is very simple. See, if we could check that this is a subspace, the right hand side, if we could check that it is a subspace, and if we also could check that it contains all the UIs, then by definition it has to be the equal to the left hand side, because left hand side is by definition it is the smallest subspace. So it is enough to check, it is enough to check that right hand side is a K subspace of V containing all UIs. But this is obvious, because you see, if you want to check that all UIs are contained there, so fix an I and you can take vectors in I. They are obviously the finite sums. Vector itself is a, so singletons. So singletons, therefore all UIs are contained here. Now to check it is a subspace, you have to check that two elements of such two elements in the right side, their sum is also there. But if you have two finite sums, it is again a finite sum, so it is there. The scalar multiple is also for same reason it is there, so it is a subspace. So with this I would like to end this lecture and continue next time. Thank you very much.